Good morning, good afternoon, and good evening, everyone. I realize there's about 1,400 people here, so hopefully I covered all of you guys. My name is Haroon, and this workshop is going to be about deep learning. So, which is interesting because we had quite a few issues, technology issues, but deep learning, that's what we're going to do. So, just a couple of housekeeping items I want to tell you guys. As much as this is a lecture, it's also about you guys. So if at any point you have a question about any topic I'm covering, feel free, come off mute. I will also be checking the chat. I can't promise I can see every single thing, but definitely you can post questions in the chat, or you can just come off mute, and I'll be more than happy to answer them. All right. Any questions on that? Let's go ahead and get to the good stuff. All right, deep learning. So let me go ahead and share my screen here. Oh, great. Give me 1 second. It's asking me all this stuff. Yes, allow Google Chrome. Thank you. Okay, so let's go ahead and share this. Okay, so I think all of you guys can see my screen, right? Okay, so oops, let's get this out the way. All right, and so here we go. So again, today's topic, deep learning with PyTorch. So here's kind of a quick agenda of what I had planned. I want to give you guys an overview of deep learning. I kind of want to break this out such that I want to spend about half the time talking about what is deep learning conceptually. I think once you guys are able to understand how deep learning works, using it, and of course, seeing it in code is going to be a lot helpful. So again, the first 20, 30 minutes or so, I want to talk about deep learning. And then the latter part of the course, I want to show you guys how you can use PyTorch, a library within Python, to create a deep learning model. Okay, so before we even get into what is deep learning, why should you care, right? So there's a country across the pond, China. Sorry, you didn't hear that. There's that country, and they are setting incredibly aggressive goals for AI, right? And so they are utilizing these kinds of technologies, deep learning, especially all different types of machine learning algorithms. But why is that necessarily important to you, right? Well, if you are a leader in your organization, maybe you are a business leader, maybe you work for the government, maybe you work for a nonprofit, I guarantee you the next wave in technology, the next advancement is going to come through AI. And specifically, one of the tools could be deep learning. And so if you want to stay relevant in the business environment, in government, this is something that you need to think about. You definitely need to consider. China has set such incredibly aggressive goals by 2030 that they want to basically reinvent all the things that you see today with AI. And so if we want to keep up with that, and if we want to be leaders in the business environment, in our governments, if we want to be those leaders that we are today, we need to adapt, and we need to understand how these things work. And just to give you a small example here, if any of you guys are fans of the board game Go, right? So Go is a super old game. It's about 2,500 years old. And so a few years ago, the creators of a neural network, AlphaGo, they created that network that finally beat Lee Sedol. And the way the computer did it is by finding a complete novelty that had not been explored. So think about that. A game such as Go, that it's 2,500 years old, and it found a move that humans could not have thought of in a matter of seconds. That's the kind of pace that we're talking about here. That's the kind of power that deep learning has. In just a matter of seconds, it compacted everything that humans have done in this game, 2,500 years, gone. So these are kind of the advancements that you guys should be thinking about as it pertains to your domain. Does that sort of make sense? Why this is so important? And I can share some links if you believe in Yale. They have their Harvard, I believe. They have their Belfer Center, and they talk about how China is potentially beating us in AI. Again, this is not to be a geopolitical thing. It's more about staying relevant and how we. So I come from a consulting background. How we stay relevant in terms of a business environment maybe some people out there work in the government. Maybe you're a student, right? And you want to learn something that keeps you relevant, that pays you a salary going forward. This is why this is so important. Any questions on that? Okay, so let's go ahead and get into deep learning. And for this, I will do some, okay. I think everyone should be able to see my screen here. So deep learning, so if we have the whole domain of AI, right? So think of this as the whole expertise in AI. And we have within AI a subset called ML, machine learning. And within ML, we have deep learning. So deep learning is a subset of machine learning. Deep learning is a type of machine learning algorithm, which also is part of the AI domain, okay? And so the simplest explanation that I have found for deep learning, it's really this. So let's add oops, get this out the way. So my favorite definition of deep learning is this. Oops, and I think I made that way too big. Actually, let's get rid of this. I'm sorry, struggling a little bit here. There we go. That's what I wanted to do. And let's zoom that back to 100. Okay. So deep learning is a technique for a computer to automatically find representations in data. That to me is the simplest definition of deep learning. A technique for a computer to automatically find representations in data. Okay, so let's explore this a little bit. So let's go move to the side here. Okay, so it used to be that, so let's do some illustrations here. So here is my data. Oops, sorry about that. Here is my data, okay? And the old way, it used to be like this. So I have all my data in this container, and I have an expert, right? So here's my friendly expert, okay? And the role of this expert was to create features, i.e. feature engineering. So let's say we have data of a picture, a portrait, right, of a person. So what this expert here, let's call him expert, what this expert would do is say, oh, okay, this is one feature. This is another feature. This is a third feature, so on and so forth. And so if we're talking about portraits, maybe feature 1 is eyes. Feature 2 is hair. Feature 3 is a mouth, etc., etc. So in the old way, this expert, he would have to manually tell the computer, oh, this is something called an eye. This is something called a nose. These are features of what you're looking at. And this is how you define it. It looks like this pixel, that pixel, so on and so forth. Okay. And so once he did that, then finally he could put all this into his ML algorithm, and then he would get some kind of output. Okay. Now, how does that differ from deep learning? This is the cool part. We still have our data, right? So we have our little container, but there's no more expert now. All we need to do is feed that data into, here's my magical black box. Because that's really what it is. The computer is automatically going to look at this data and say, oh, I know that this is a feature here. I know what this is. I don't know what it's called, but I know that this looks like something called an eye. And we'd have to go in and verify that. It picks those features out for you automatically. And so the computer takes care of the expert's job. Does that make sense? Any questions on what we've talked about so far? This is why deep learning is so powerful. We don't need this expert. We don't need this SME here on the left. We just give it to the computer and it figures it out. Yeah. Okay, so let's continue. I'll take silence as golden. Okay. So as I was thinking about, hey, how do I how do I relate an example of a neural network, right? I thought, well, why not do baseball? Because when you think of deep learning, you think of baseball. Now you probably think of steroids. Anyway, the Atlanta Braves, right? Big Braves fan. Hopefully they win tonight, right? So here, let's kind of build a simple neural network that has one input and one output. And we're going to base this model on the number of fans in our stadium. I know it's a bit of a simplified example, but I think it will drive home the point. So we have a list of our number of fans. And for this example, we're just going to define a random weight. It does not matter what it is for demonstration purposes. You'll see why very soon. Okay, so again, and Ted Turner, if you're out there, please hire me. We have a model that takes in a number of fans and with a weight is going to predict their winning percentage. Okay, so let's run this. So here we are going to define our neural network function, and our function is going to be, our prediction, sorry, is going to be based on the fans multiplied by the weight. Is everyone with me so far? Again, simple neural network. Okay. So let's go ahead and see what this very basic neural network looks like. So let's just take in this first example. So we have 10,000 fans, and we have a weight of, that looks like for 10,000ths, if I could read correctly. Yep. So what this is saying is our neural network, according to these parameters, has a 40% prediction. Okay, it's not that great, but the key point that I want you guys to take from this is in a neural network, you have one input, you have a weight, and you have an output. So let's go back to the drawing board a little bit. This is the picture that I want you guys to have. You have an input and you have an output. So let's have this as input, output, and you have something called a weight. This is the picture that I want you to, and let's kind of block this off a little bit. This is the picture that I want you guys to have in your mind as we talk about this. Okay. However, we're a little bit more complicated than that, right? So it's not just fans that are in the stadium. Maybe we can add some more inputs. Maybe we can add the win-loss percentage for the last 4 years. And then maybe we can also add players with a batting average of 300 or greater, right? So let's go ahead and now incorporate these extra inputs into our version 2, into our version 2 of our neural network. Okay, so now we have multiple weights and we have multiple inputs. So the first one, of course, number of fans. Then we have the win-loss percentage the last 4 years. And we have players, the number of players with a batting average of 300 or above. Okay. Is everyone with me so far? And again, feel free to come off mute and ask a question. This isn't meant to be, me just blabbing up here. I definitely want to hear from you guys, and don't hesitate to stop me. Okay. Very similar to what we did upstairs, where we said, hey, this neural network is going to have an input and a weight. Well, it turns out just because we're adding more inputs to our model doesn't actually change that calculation. Okay.
Haroon,
what is that? Yeah.
I'm interrupting really quickly. Folks are asking for the link to the notebook.
Oh, this is
you're open to sharing.
Yeah, absolutely. I can send that. Thank you for stopping me. I can send this notebook at the end of the class, or I can email it out however we wish. This one, and I can also export this out, these drawings, not a problem.
Perfect. We want the drawings too.
Okay, no problem. No
Thanks,
problem.
Haroon. Sorry for interrupting.
No, you're good. No problem. Okay. I apologize, guys, because I don't see necessarily your chats or your questions. I'm just looking at the screen. So again, don't hesitate to come off mute. You're not going to interrupt anything. Okay. So similar to what we did upstairs, where we have, hey, to calculate this prediction, I have an input, fans, and I have a weight. Well, we can do something very similar here. The only thing that's changing is the number of inputs and the number of weights. Okay, so here we have 3 inputs and then we have also 3 different weights. And so what we want to do is calculate a weighted sum of all those inputs. So let's kind of see this in action. So here's my function for a weighted sum, right? So again, I want to put your attention to this line here. What this is saying is, hey, for whatever's in A, multiply it by the corresponding index of B, right? So in this first example, so let's take a look at it. Here are our inputs. We're using number of fans. So let's go back here. Let's just copy this so we don't have to keep scrolling. Yep. So what we're saying here in this very first instance is, okay, let's take 10,000 fans. Let's take a 40% win loss. And let's take one player with a batting average of 1. And then where are the weights? The weights are going to be this guy. These are going to be our weights. So what is that calculation going to look like? Well, 10,000 times that, and then 0.4 times 0.1, and then 1 times that. Is everyone seeing this conceptually, a weighted sum? Okay, let's keep going. So here is now our new and improved neural network. So it gave us a slightly better result, right? Instead of 40%, maybe 40% and a bunch of decimals. Yeah. So what we just did here is something called a dot product. In other words, we took 2 lists or vectors, we multiplied them together, and we achieved a weighted sum. Okay? If you can understand this math here, then you have just now understood how a neural network works. I'm going to repeat. If you can understand the math that's happening here, then this is the key for all the math required of a neural network. Of course, in this very simplified example, we only have 3 inputs and 1 output. But if you extrapolate to multiple inputs and multiple outputs, the math is always going to stay the same. When you hear people say, oh, this deep learning model, it's taking me hours upon hours to run, well, this is the reason. This is a computationally intensive, can be a very computationally intensive process where you need to multiply your inputs to the different outputs and all the different weights that go into it. This is why it can take so long. But as long as you can understand this basic math here, this is how a deep learning model works. I want to take a pause here. I feel like I've been blabbing too long. I want to field some questions. No, nothing? We're all getting it? Really? I'm doing that good or I'm doing that bad? Let's see. Autograph simply doing the first one. Is this improvement within random error? What do you mean by that, Mahmoud? Is this improvement within random error? I think I'm going to answer your question in just a minute here. I think I understand where you're going. Okay. Okay, again, what questions do we have? Because I know I'm not doing that great. Or maybe I am, I don't know. Okay, I'll go ahead and take silence as golden. So up till this point, we dealt with networks that are 1 input and 1 output, right? But you can extrapolate that example for all neural networks, right? So I'm sure you guys have seen a diagram like this, where you have 3, something very similar where you have a bunch of inputs to the left and a bunch of outputs to the right. And you see all these arrows, right? Think about the weights. These are the weights of each of these inputs, okay? So more common is having a matrix of weights, right? So in this specific example, we have 3 inputs, and all of those inputs, are going to have their own individual weights. So really, it's a matrix. Think of it as a matrix, a 2D matrix. You have, think of this as an input, right? This whole thing is an input. And then within each, you have the different weighting of that input going to a different output. This general structure here is called a matrix, but maybe you guys have heard the word tensor, right? And so you can have, I'm sure you guys have seen a vector, right? A vector is a one dimension, right? You can say as a simple list. A matrix, you can think of as list of lists, not red pill, blue pill, but list of lists, right? And then you can go further. You can have a three-dimensional, right? You can have 4-dimensional, 5-dimensional, 6, as many dimensions as your data allows, or as many dimensions as you need. Is this making sense so far? Okay, so probably the most common neural network image you've seen is something like this, right? So you have all this stuff and all these lines coming back and forth. And so what this is, again, if you understood the math from upstairs, you now understand this. The only thing that's changing here is the addition of these layers. These are called hidden layers. So in this example, so let's take another slice here. In the original example, right, we just had something like this. And then we had something like this. And we had, here's our output, right? Those were the three features, win percentage, batting average, and number of fans, right? And here's our output. Well, we can then turn around and have this output feed in to another neural network. So maybe this goes into here, here, and here. This is how neural networks are layered. Maybe one layer is not enough. Maybe we need multiple layers, right? So again, how would that look? Let's just start very simply. We have 3 inputs and we want to give it to, let's say, another 2 outputs. And then from there, we want to go to another 2 outputs. This guy right here, that's your hidden layer. And when you see diagrams like this, the takeaway that I want you to have is, okay, this is just a network of neural layers. This is going into this first, doing some kind of function, doing some kind of feature engineering, whatever, and it's going in, finally, it's spitting into this. So here's the input, here's the output. Now it's turned around, it's an input, and then this is the output. Finally, this is the, I guess, true output, if you will. So when you see the term layers in a neural network, these are the layers. Let me take a pause here. Any questions? Okay.
Haroon, really quickly.
Yeah.
So I'm the only one who can like be off mute. Unless
That's why. That's why the crowd's quiet.
Yeah. So where they're going to ask the questions is in the chat. So a lot of them have been kind of answering one another's questions, which has been nice.
Appreciate that.
But yeah, we'll want to. But if someone, Haroon's pretty open to interactivity. So if anyone wants to come on screen at any point, drop a line in the chat, and I'll bring you up.
Yeah. Okay.
If you're up for it. Okay, just wanted to let you know.
Yeah, no, good to know. And if it wasn't for that, so let's see. I could probably do a better job of looking at questions too. And
it's hard to do both.
Yeah, it's a little okay. So maybe
I could always, you know what? I could always jump in when you say like, does anyone have any questions? I can ask any questions that are out there. You want to do that?
Okay. Yeah, let's do that.
All right, sounds good. So we have one right now.
Go ahead.
Danielle ask, why do we need the layers? What's the purpose of putting it through additional functions?
Yeah, great question. So it could be the case that having a one-to-one, so let's go back here, and it could be the case that having a one-to-one, oops, wasn't drawing, sorry about that. it could be the case that having a one-to-one of input output, it actually does what you need it to do, but more than likely it doesn't. And so think of the layers as it learning, it fine-tuning your predictions. So you could get what you need just by having one layer, just one input and one output. But most of the time in the real world, especially when you see neural networks, they're built upon layers. And those layers, what those represent really is fine-tuning the model. That's why you see that's really why you see neural networks with multiple layers. Very rarely do you see a neural network with just one layer like this. Many times you need hidden layers that make computations off computations off computations. Does that make sense, Danielle? Let me see back in the chat.
There'll be like a 5-second delay. Okay, now we've got a lot more questions. Danielle, did that make sense? William asks, yes, she said it does make sense. Thank you. Good question, Danielle. William asks, is there a dot product between two layers?
Yes. So the cool thing about this neural net, about having the layers is, and unfortunately for this presentation, I'm not going to get too much into the activation functions, but yes, you can have different types of activation functions within your layers. In one layer, you can have something like sigmoid function. Another layer, you can have something else. It allows you to fine tune how you want to understand the data. Yes, there's a whole host of options you can perform within each layer to interpret the data that came before it. Yes. And I see a question from Mahmoud. Does that mean increasing the number of layers would further refine? Yes, great point. So one of the problems you probably heard is overfitting, right? And so overfitting is absolutely applicable for neural networks. You could have too many layers and the model knows what the data looks like, but to its own detriment. And so that's something that you need to be careful of. That's something that you need to consider. Hey, am I still getting the same output if I have 5 layers versus 4 layers? And maybe if that's true, maybe you want to peel back a layer. You can, just like all machine learning algorithms, this is definitely prone to overfitting. Absolutely.
And then Maha asked a question. She said, would layers be similar to creating parallel universes to see which ones?
Creating parallel universes.
Yeah, that was
like
an interesting analogy.
Yeah, like Rick and Morty. Yeah, let's go to parallel universe. Anyway, I would have to know more, Maha. I'm not really sure how to answer that. Would layers be similar? Yeah, that's a good question. Layers be similar? I don't think it's parallel. I think it's I interpret it more as further data processing. Let's see. And then, what's a good way to say that? Sorry, go ahead.
Oh, no, go ahead. I was going to ask.
Yeah, I think it has to do with more processing. Now, what's the end goal? And I'm going to talk about this in a second. We want to reduce our error as much as possible, ideally at 0. And so when we have that goal in mind, that's kind of why we build these layers. Maybe in the first layer, we don't get to a good enough error number. And maybe we need to create more layers to slowly but surely reduce our error as much as possible. Yeah.
And then William asks, is the function always differentiable under this design?
Always differentiable under this design. I think you mean like, can we always have different functions? Yeah, absolutely. You can create your own layer. You can specify how many neurons it has. You can specify what function to use. Absolutely. PyTorch, TensorFlow, they all allow you to do that. Unfortunately, that's not the target of this workshop, but absolutely to your question, you can always define, and you can define specific layers and have it. And I'm actually going to show you that when we go to the PyTorch section, how AlexNet and ResNet, how they're defined. I think once you see that example, it will make a little bit more sense.
Okay, let's head there, and then I'll keep an eye on the questions.
Yeah, cool.
Thanks, Haroon.
Yeah, I love the questions, guys. Keep them coming, by the way. Okay. So up till this point, all we've really talked about is an input, a weight, and a prediction, right? We haven't really talked about this weight thing. And so now let's jump into it. Let's talk about the weight. Okay, so I'm going to switch gears here a little bit, and I'm going to define some parameters. I'm going to have again, this is a neural network. I'm going to have a weight of 0.5, an input, and a goal prediction, right? This is what I'm trying to predict to, okay? So again, our prediction is 0.25, but our goal is 0.8. MSE, mean squared error, right? So how do we check whether we're on the right path? MSE, mean squared error, is just one way, probably a more popular way, but it's just one way to check how much error is within our model, right? And so if we want to get close to our goal, we need to reduce the mean squared error. Now, your first question might be, okay, why are we squaring the error, right? And so let's break this down. I'm looking at line 14 here. The error in MSE is defined as your prediction, right? Versus your goal, sorry, minus your goal squared. The analogy that I like to give here is, say you're shooting a basketball, right? And you're trying to hit you're trying to make a free throw. Does it really matter if you miss 1 foot to the left versus 1 foot to the right? No, you still missed it by 1 foot. And so the goal here is, let's take out that direction. Let's take out that negative direction, positive or negative direction, and square it so we can have one number. Because again, it doesn't matter that we were wide left or wide right. We just know that it was off by 1 foot. And that's all we really care about. And that's all what the machine cares about too. When you introduce negatives, you'll see why in a second, it can kind of play a little bit havoc with your model. Okay. One way that we can kind of figure out, hey, what is the best way to find a weight? We can kind of do something like a brute force method, I feel, called hot and cold, right? So in this example, you can see that our weight is 0.5, right? And our input is 0.5, and we are trying to get to 0.8. But our prediction right now is 0.25. So it's way off, way off, right? So one way to reduce this error and get closer to our goal is by increasing the weight by something called a learning rate. And I want to put your attention to this line here. What we're saying here is, okay, let's kind of see if we're getting hotter or colder once we add a tiny amount to our weight. And this tiny amount is represented by the learning rate. So here, let's see what happens when we increase our weight, right? So, okay, our prediction is 0.3, our goal, okay, so it looks like from the last model, we got just a little bit closer. Okay, that looks good. Now let's see what happens when we decrease the weight. Okay, we're getting further away, right? I think you guys can see that our prediction is now 0.2, which is less than what we had in our initial 0.25. We're getting further away, and our error went up. So what I'm trying to show you guys here is one way to calculate, hey, what is the best weight that I need to use? It's kind of this brute force method. Let's just increase the weight, by a small amount. Do we get closer? Do we get further? And we can further tweak what happens after that. But I think you guys will agree that this isn't really efficient, right? If you had to continuously guess and take these small itty-bitty steps, first of all, it doesn't tell us how much to move. It only tells us if we're getting hotter or colder in terms of closer to our goal or not closer, right? But in this case, we want to actually get to that 0.8. And so it's possible that we could just overshoot it or undershoot it. Does that make sense? I want to take a pause here. Are we all following along with the learning rate? Let me see in the chat here. Yep. Okay, not seeing too many. Okay, I'm going to go ahead and keep going. This is just but one way to find the optimal weight of the model. However, there is a better way, and it's called gradient descent. Now, it sounds kind of a scary word, but I promise it's not that bad, okay? So let's go ahead and use the previous example and modify it a little bit, okay? And so here, again, I have the same weights. I'm going to iterate through my model about 20 times. And what I want to put your attention to is these two lines here. This is where we're going to do something a little bit different. In the last example, hot and cold, we were just finding the direction that we need to go, right? Here, with gradient descent, we are not only finding the direction, but we're finding the amount to go to. I'm going to repeat. With gradient descent, we are going to find not only the direction, but the amount that we need to get closer and closer to our goal. And so when I run this cell, right? So let's kind of look at it line by line. I think it will make sense. Initially, our direction and amount is 0.275. Our updated weight is 0.775. And our error is this, and our prediction is that. But what's happening as we go further, right? We're getting closer. 0.25, 0.38, then 0.49. See how it's getting better? It's able to understand, oh, okay, you're giving me some kind of a direction to go, right? Which is go up in terms of weight, and it's telling you the direction to go. Sorry, the amount. And so we can see that, okay, after 20 iterations, we actually do get fairly close. So 7.72, 0.74, 0.75, and finally at the last iteration, 0.79. Again, the math behind this is these two lines of code. So here we are taking our prediction, subtracting from our goal, and multiplying it by our input. And then finally, we are subtracting that amount from our weight. And that's how the weight continuously readjusts and adjusts and adjusts again after every iteration in the model. I want to take a pause. Any questions? Let's see. Are they looking for grade? Yes. Okay. So William, yeah, this is a good question. So in this example, we are using MSE, right? So we are looking to minimize squared error, but there's other ways to, there's other error methods too that you can use. Okay. Let's keep continuing. Okay. Again, these are the two lines that I want to kind of bring to your forefront. This is what's enabling us to improve our model, okay? We're able to control, hey, if the input is 0, then direction and amount is also going to be 0. If it's negative, we want to make sure that we want to correct for that. Even though the direction might be negative, we want to make sure the weight gets corrected for that. And if, again, scaling, if the input is going to be big, then the weight update for that input should also be big. So the best way to kind of show a gradient descent is with this graph or something like this, right? So in the very, very beginning, we are having some kind of error, right? And it doesn't matter really where, and we have some kind of weight. And what the computer does behind the scene is, hey, I need to get to here. Because here, when the slope is 0, that means my error is at its least. You see, is everyone kind of seeing that visually? When you get to here, this slope, that means the slope is going to be flat and the error is going to be at its absolute minimum. This is what we mean by a gradient descent. If all you get from this is just this graph, I think you're in a pretty good spot. This is what's happening behind the scenes, trying to get to this minimum value. The goal is for the computer to play around with this formula until it finds a weight where the error is 0. Put in a slightly different way, there's a relationship between these two variables, the weight and the error. In mathematical terms, the derivative, remember that word all the way from back when? It's back again, better than ever. The derivative quantifies this relationship. But again, I don't want to go into that rabbit hole if we talk about calculus and all that, it's really not that necessary. If you can see this conceptually, you can then understand, oh, this is what the computer is doing behind the scenes. Again, here's a little bit more of a representation here. If we're starting from here, right, if our starting weight is 0.5 and our error is this, we want to get to where the error is going to be 0. So here's what, and I probably should make this a little bit bigger. Here's what neural networks boil down to. A bunch of weights you use to compute an error function. And there is always a relationship between any weight and error of the network. Once you understand the relationship, you can change each weight to reduce the error to 0. That is the whole goal of a neural network. Let's get the error, reduce the error as much as we can to 0 through this iterative process. I know it's a very kind of a simple process, at least in terms of this model, but this is absolutely applicable to all the neural networks that you'll see out there, all the complex ones. Okay, so I know we're kind of getting close to the time. I know we did start a little bit late. So I want to take a quick break here and answer some questions. So let's see. Oh, okay, Timothy, thank you. Yeah, yep. That Coursera course is gold. It's amazing. Yep. Okay, that seems too many questions, but I see a lot of chat. And that's good. You guys are talking to each other. You guys are answering questions. That's awesome. Okay, so the rest of this course, this workshop, why can't I click? Here we go. I want to show you how you can today deploy a model within a matter of minutes. Okay. Oh, I had this example. If I have time, I can show you guys that. So there are tons of libraries out there to create models. Why are we using PyTorch? Well, in short, it's flexible and it's Pythonic. If you're comfortable with Python, you'll be right at home with PyTorch. Great documentation. Probably the biggest one, and I know TensorFlow can do this too, but computations can be offloaded. So you don't have to worry about, you can shove all that to your graphics card. Here's an example of a project flow of, just a general deep learning project flow here, right? So let's start from the left. Here's our data source. Sample tensors. Think of tensors as, again, those dimensions that we talked about: vector, matrix, 3D, 4D, so on and so forth. Everything is going to be processed here. It's going to be compiled together in a batch. And then this is where the magic happens, the training loop. So the model is trained, and again, here's all your computers and GPUs that are doing all this work. And then finally, you end up with a trained model. Once you have this trained model, you're ready to push it into production, and then you can use it and analyze it and use it for the application that you want it to. So here in this part, and again, I know we're going a little bit over time, but I'll try to keep it short and sweet here. I want to show you guys how you can use an off-the-shelf network to do some image detection. Okay, so let's go ahead and do this. I'm just importing PyTorch here. I'm just checking my versions. Okay, so let's go ahead and import all the different models that are available to us in PyTorch. So you can see AlexNet, DenseNet, GoogleNet. Maybe some of these you guys have heard. For this example, I believe I'm going to use ResNet. It's a very popular model. It's an award-winning model. It's very good. But these are all the list of models that you have off the shelf that you can run today within Torch Vision. Okay. So let's go ahead and create an instance. Oh, I guess I'm going to do two, AlexNet and ResNet. I forgot. So here, let's go ahead and create an instance of AlexNet. And I think the question came up earlier, like, okay, what does AlexNet look like? Or how many layers does it have? And so AlexNet, again, is a very popular model. And here's what it looks like graphically. So you start off with 96 neurons, go to 256, 386. It does all these computations. These are all the different layers of AlexNet. And if you want to see that in text, well, here's what it looks like. I prefer the graphics. Okay, so, and then let's also look at ResNet too. Again, here's what it looks like under the hood. These are all the different layers, right? Here's layer 1. I believe ResNet has about 10, no, it has more than that. I think it's 100 layers, yeah. So here's layer 1, and then you'll see layer 2, and these are all the different parameters for layer 2, and then, let's go all the way to the end there. Let's see. Yep. Again, these are the layers that are created in ResNet. And here is the example that I'm going to show you. So I found a random image of a dog, and I'm going to ask the computer to basically analyze this picture and tell me what breed it is, okay? So again, I'm going to take a dog image. I'm going to do some pre-processing here. I'm going to pass it into my model. And then I'm going to basically grab the score. What score did that picture give me? And then I'm going to finally classify it in terms of a label. Okay, and again, this notebook will be available for you guys, as well as the drawings. So fret not. I'm going to go through this part a little bit fast just because I have this kind of compiled already. And I don't want to get too much into the details here, but suffice to say, you will have this and you can tear it up and play with it on your own. Okay, so here is where we're going to do some data pre-processing, right? Maybe you've heard that term. Basically, we want to get the data ready for it to be acceptable to the model. And so we do this pre-processing. I'm just going to go ahead and run this. Here's the image that I found. It's looks like a golden retriever, right? Or maybe, I don't know. So again, this is the image that we're looking at, that I found. And we're going to ask ResNet, hey, tell me what kind of dog this is, or give me a label to what this is. So here's where we do our pre-processing. Okay, I'm just going to go through with this a little bit. Here, what I'm doing is I'm putting the network into evaluation mode. I want to evaluate the results based on this image. So here's what the evaluation looks like. Okay, again, it's not that important to see what's happening here. It's more about, hey, I'm just putting this model into evaluation mode. So here, this batch T, it refers to this. So we've reshaped, we've cropped, we've normalized our data, and we put it into the tensor that's needed for ResNet to understand this image, okay? And so let's go ahead and run this. And this is what the data looks like in floating point numbers. Very exciting, right? Lots of numbers. But again, this is what's happening behind the scenes. Think about the example that we talked about 30 minutes ago, the mathematics behind it. This is exactly that calculation. And so here now we've passed it to our model. We've pre-processed, we passed it to our model. Now we're ready to get some results. So with ResNet, you have a bunch of classes. There's a text file. When you use it, it has basically a list of all the labels, right? And so here I'm just importing a list of the labels. You can see the labels if you want. I believe it should just be, yep. So these are all the different labels that are identified in this model. So yep. So here I want to get the max value of our image, okay? You'll see what that means in a second. And so now I want to figure out, hey, what do you think this image is based on a percentage? This guy. So it turns out, according to this model, it's a Labrador Retriever. And it's about 89.47% confident it's a Labrador Retriever. And then here I'm just getting the top 5. So Labrador Retriever, Golden Retriever, Chesapeake Bay, tennis ball, funny enough, and Greater Swiss Mountain Dog. you can use this model today. I can send you guys this model, and there's a lot of resources on ResNet and AlexNet. This is something that you can incorporate today. Again, let's think back to why we're even interested in deep learning. If we're not able to understand how deep learning works, how are we going to use it? And you can bet your competition, whoever that is utilizing deep learning to solve problems, right? Think about the AlphaGo example, right? We want to be the human being in that instance. And hey, the deep learning model was able to come up with a novelty that had not been found for 2,500 years. Think about that. We've been looking at, we've had the modern stock market economy, so for maybe less than 100 years, right? I'm thinking back to like the 1930s. And so what kind of insights can we potentially uncover with a neural network? This is a possibility that I want you guys to think about when you think about neural networks. Hey, I have this data in my domain, with whatever expertise you're in. What could this look like if I run it through a neural network? What are some of the insights that I could find by running it through a neural network? That's what I want you guys to take away from this. And the tools are out there to do this, but it's really a matter of you guys wanting the motivation, and B, you want to stay competitive, right? This is something that businesses think about all the time. How can AI, specifically deep learning, how can we use deep learning to provide more value, to be more profitable? What are some of the applications that we have already with deep learning? Chatbots, computer vision, right? Self-driving cars. Those are going to be the forefront, within the next 10 years. And so that's why I think it's incredibly important that you guys understand, hey, this is the math in a very general sense. This is the math that's happening behind the scenes. And this is how I can use a model today and apply it to my work. Now let's take a pause here. What questions do we have? Maha, what are some practical enterprise examples? What are some of your most favorite? Yeah, so neural networks, actually, unfortunately, I have not been able to use in an enterprise setting. I've used other models. I've used k-means. I've used reciprocal regression. Sometimes that works just as well. I've used a bevy of clustering models, but not yet neural networks. So once I have that opportunity, you can bet I'll grab it. Neural nets can use anywhere you would use it. Predict. Yep. I agree with that. Yeah, I think we're actually right at the time, because I think we started at about 50 or maybe 55, and it's about that time. Yeah. So I can go ahead and stop share. How do I stop share? There we go. So that's pretty much all I have for you guys. I hope that was educational. I hope that was informative. I hope, again, what you took away from that is deep learning, it's not necessarily the mystery that it might seem. Once you understand that math, in terms of we have an input, we have a weight, and we have an output, once you understand that basic mathematical structure, that's how all neural networks work. And that's really what it is. Once you can kind of understand that and see that, oh, I can just go right now off the shelf, import a few models, and start running something, that's what I want you guys to do. That's the motivation behind why I'm doing this talk. I think it's incredibly important. In some aspects, we're a little bit behind, I feel, but again, don't want to get into the geopolitical, it's irrelevant. I just look at it from a purely selfish standpoint in terms of, hey, what do I need to learn to continue to be relevant? What do I need to learn to keep pushing the boundaries and adding value, right? To your organization, to your business, to the government, right? For example, if you work in the government field, that's what I really want you guys to take away from that. So yeah, any last questions or parting thoughts? Yeah, I like that. Yes, give me the break. Yes, exactly. I'll run all the machine learning models. Exactly. Ted Turner, please. Thank you. No questions. Nothing. Come on, someone. Okay, fair enough. Thanks again, everyone. I really appreciate everyone's time. Again, I will post all the notebook and my drawings. I will post them up there for you to have. Thank you and have a great rest of your day, everybody. Bye.